Sir, it's saying visitors are in this because it actually looks for the exact domain name. That is why it is not allowing YouTube streaming. That yellow one.
Okay. I am trying again. Let me check.
It's happening just because of one person, I think, Prasid, but he's also ITM student, so it's
Yeah.
because
But
of that.
I joined off before also. At that time, it
Yeah.
was working.
Yeah, I don't know why you are using the regular ITM. We are all using this online thing.
Like
So,
before,
yeah.
I was using, if there is Wi-Fi issue, I don't know it happens or not, but before I was using my mobile Wi-Fi. Now I am using IIT Wi-Fi.
It's still showing you as a visitor.
So while using IIT Wi-Fi, I don't know. Email
Yeah.
ID, SML ID is same.
Yeah.
By the way, I am outsider for this class.
Okay, we started again. Let me check. It will run or not.
It's like inserting an element to a tree. Okay.
It start actually, but after 10-12 seconds, it closed. Yeah. Okay, so now I'm recording this session, so I'll upload this later. I don't know what happened. Okay, so good evening, everyone. Welcome to week 10 open session today. So I hope, so I think deadline is tomorrow. So I hope you have watched the video, you have solved the assignments. So can anyone tell me what topic you are facing difficulty in this week? Or do you want to just start from the first topic? Okay, no answer. Am I audible?
Yes, sir. So you decide.
Okay. Okay, then we will start from the first topic, and then if you have any questions or any doubt in this, then you can ask in between. Let me share my screen. Okay, so in week 10, basically we are learning the string matching algorithms. So as you all know that what is string matching, we simply match one string to the another strings, if it is matched or not, or if any particular part of small part of the strings we want to find out that in the another document or in another strings, big strings. So there are many applications we generally used based on this topic, string matching. So one most common example is when we works on the any doc editor like Microsoft Word. So sometimes we just apply the search, okay, Control F, and we just search any word in our whole document. Okay, so that things actually what happen internally when we just perform this operation. So how this operation performed quickly. So there are many methods. There are naive approach, but how generally this operation performed quickly. So because of that, we are learning these algorithms. Otherwise, this is a simple topic. You can simply compare character by character into the strings, and you can check your string is matching in the another strings or not. So this is the main idea of this week, string matching. So there are many applications like plagiarism. If you know that plagiarism, when we check plagiarism in any documents, if it is copied from the another documents or not. So that application also use this string matching method. So there are many ways. So we will start from the brute force approach. Okay, So what we are just doing that, we are just taking one strings, or we can say that one text. Okay, so the size of text may be very big, and we are just taking one pattern. Okay, pattern means very small part of the strings, and we want to find out that that pattern, in what place this pattern is actually exist in our text. So this is the main goal for each algorithms. We want to just find out the index where our pattern actually matched in the text. So first, brute force approach. So as you know that the brute force approach is simple. If we have two pattern, sorry, text and patterns, so we can simply compare from the starting, and like here one example is given, and this code is given. What code is doing actually? So suppose, so if you see this example, so this is the pattern, long pattern, and sorry, long text, and this is the pattern AB. So if we want to find out this, so what method we can use? So we can simply start comparison from the first index. Okay, so we will just simply put this pattern from the starting of the text. Okay, and then we will start comparison character by character. If it is not, any character is not matched in between, so we will shift our pattern to the next, only one position next, to the right. Okay, so suppose if we are, I'm just writing the small part of this, like B, A, B, A, B, B, A, B, A. Okay, so I just written till here, and I'm just starting like this, A, B, A, B. Okay, so we will just take two pointers, like one for the pattern and one for the text, and we will use this pattern, like if I'm taking I for pattern, so this is pattern and this is text. Okay, and J for like text. Okay, so then we will initially both are 0, so this is starting from the 0 and this is also 0, and we will simply comparison of each character A. If characters are matched, we will move to the we will increment both I and J to the next. Okay, okay, so say B. This is also matched. Second character is also matched. Then we will increment the both character. Third character is also matched. Then we will increment our pointers. Then fourth character is also matched. Okay. So once our pattern length is complete, then we can say that our complete pattern is matched with the text index 0. Okay. So where we start from the text, actually, we start from the 0 index in this case. So we can say that our pattern is matched at 0 index. So we can just store this information in our output list or any place. And after getting this one matching, we will shift only one position to the right, like here, A, B. Okay. Now we will again, we will just match the first character. So A, B. Now first character is not matched. Okay. So you can see this B and A is not matched. So if first character is not matched, then our pattern will not match completely at this place. So once again, we will shift our pattern to the one position right. So like A, B. This is the third. Okay, so at this position. So once again, you can see this A match, B match, and A match and B match. So now all characters are matched. We will note down this index. So this is the second index. Okay, same things we will repeat to the complete text. After if a character is not matching, we will shift one position to the right. If our complete pattern is matched, still we will shift to the right only one position, but we will note down the matching position. So you can see in the output 0 we are getting, 2 we are getting, at 7 index on the text we are matching our pattern, 14, 16, all these place our pattern actually start matching in the text. So this is the naive approach. So in general, what is the length of our pattern and what is the length of our text? If we just take this value n or m, so we can say that our complexity of this will be n into m. Okay, because we are comparing each character one by one, then we are shifting only one. So we are traversing whole length of the this text, and also we are comparing each complete length of the pattern with the text each time.
Say, so we'll get all the occurrences of the pattern in this.
Yeah, all the occurrence. Okay, so where actually this pattern is matched in the text.
So there are
all-
two loops. So there are two loops. Outside loop is going to run n times, which is length of the text, and the inner loop is actually going to run m times in the worst case when there is a match. If there is any one thing missing, then it will break the loop and increment I. Basically, the max is n, outer loop is n, inner loop is m. So that's how we are getting nm.
m into n, yeah, correct.
Yeah.
So you can see this first loop actually we are running, so we are just subtracting this length of t minus length of p plus 1. So actually when we are shifting our pattern, so our last position will start from like this a b a b. Okay, so till this position we need to shift. After that there is no benefit to shift, because after that only we have only 3 characters remaining, but our pattern have 4. So it definitely it will not match.
So it will be out of index error actually.
Out of index error. So because of that, we are just starting from 0 and length of t minus length of pattern. So that actually we are using here for the outer loop. Inner loop we are running for the pattern. Actually, every time when we are just shifting our pattern position, we are just checking each character matching with the text character. So because of that, we are iterating the whole pattern every time. So this while loop is running for the pattern. So this you can see this is for the length of p. Okay, and if match equal to true. So if at any, initially we are just assuming that match equal to true. If at any place any place, if match this our character is not matched, then we just change this match equal to false, and at this place we just okay, so yeah, match equal to false. Okay, at the next iteration our while loop will break. So that means we will not check the afterward. But if after completion of this iteration, if our match equal to true, okay, after completion of this while loop, if our match still is true, then that we can say that our pattern is completely matched. So in that case, we will just store this I value in our output list. This I is representing actually a starting index in the text, okay, which is matched actually with the pattern. So this is a straightforward brute force approach. We are simply comparing each character so one by one, and we are getting this n into m. So how we can improve this? So first version actually is the same things. We are just performing by the right to left. So this is just a small modification, but still we are not getting any improvement in this. But what we are doing, we are simply so in the previous approach we are comparing this first index to last index, but this time we will compare from the last character of the pattern to the first character of the pattern. Okay. So suppose if we have this pattern again, so A B A B A B B A B A like that, okay, and our pattern is like this A B A B. Okay, so this time what we are doing, we are simply changing the character matching process in the reverse. This time we will first check for the last character of the pattern. Okay, so this B is matched with the B or not. Okay, if this is matched, we will reduce our index of the pattern and we will check for the next previous character. So A is matched, so this is also matched, this B is also matched, this is A is also matched. If all characters are matched, then we will shift one position to the right. Okay, it's similar to A.
Only inner loop is changing, outer loop is still the same. Yeah.
Yes, correct. So you can see this is same, and this time J we are setting to length of P minus 1, so last index of the pattern. Okay, and we are just decreasing the same thing. So we are matching the character by character, and each time we are reducing this J value. Okay, So this is just a reverse process, but we are not getting any improvement for this, and we are getting the same complexity n into n. Okay. Now, how we can just improve or speed up this time for matching? So there is first algorithm which is discussed. This is Boyer-Murray algorithm. Okay, Boyer-Murray algorithm, and what it does actually, it's first it pre-process the pattern. Okay, and pre-process the pattern, it just note down the for the each character in the pattern. It just uh, count the where is the last occurrence of this each character in the pattern. Yeah, Ritik, actually this is not live. We are recording the session. I don't know, every time our live stream is
Sir, I
stopped.
missed the starting 15 minute. I just joined. So
Okay,
what?
we have just started. I have just explained the brute force approach.
Okay, and the slot that allotted,
Oh,
there will not be any change, no?
I think no.
Okay, okay.
So because on the same day we have like two.
Actually, operational team have also some limitations of the students because Python is on 27th and the strength of the Python is high. They also want to
Sir,
schedule
my
the
PDSA is
approx.
on 27 also.
So actually they want to schedule the approx equal students on the each date. So
So
because of
some
that,
student got on 27 and some on 20.
yes. So they are just scheduling in that way.
Okay, so the student who got on 20, they cannot do anything for PDSA.
No, I think no.
Okay, sir. So we are lucky I got on 27 PDSA.
Not lucky. So I think those who are giving the exam on 20, they will get more time for the interim exam for preparation. Otherwise, you will be G till and or till
So
the
toughness will
27.
change?
Same difficulty, same or lower difficulty level compared to mock.
Sir, I am talking on 20 and 27. The PDSA
Both
who will
same.
give
Both
on.
same. Yeah, both same.
Okay.
Okay.
Okay, sir. Okay, you continue. Means any information you gave in starting apart from this week 10 summary? I
No, no,
missed
no, no,
that.
no, 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 no.
Okay, sir. Thank you.
Okay, so in the Boyer-Murray algorithm, we just maintain a last, we just give a name, this dictionary as a last. Actually, this dictionary contains the last occurrence of each character in pattern. What are the last occurrence of each character in pattern on that index actually? Okay, so if we just taking some example, so what is this means actually? So like A, B, C, like okay, so suppose this is a pattern, one pattern. Okay, any sample I'm taking. So index of this pattern is like this: 0 1 2 3 4 5 6 7 8. Okay, so what dictionary is this last is actually containing? This is a dictionary, and in this dictionary we are just noting down. So how many unique characters are there in pattern? Only 3: A, B, and C. Okay, and what is the last occurrence of A in this pattern? So last occurrence of this A is 6 at index 6. Okay, and what is the last occurrence of B in this pattern? That is 7. And what is the last occurrence of C? This is 5. Okay, and last character what I'm taking is A. No. Okay. So C is 5. Okay. So this is actually a last dictionary. Okay, so after computing this information from the pattern, we can take some benefits.
So the recording of this session will be available when?
By tomorrow afternoon.
Okay, sir.
So tomorrow in morning or in evening?
No, afternoon I will upload till afternoon, because
Okay, sir. Thank you.
maybe after 3-4 hours I'll just receive on the mail. Then it takes some time for the upload. Yeah, tomorrow till
Okay.
12.
Okay.
Okay, so this is the first part of the Boyer-Murray algorithm. First, this computing this last information. After that, we just use this information for the shifting process. Okay, when we just start comparison, if any character is not matching in our text or pattern, so how many shift we need to require according to this last informations. So we'll just take some example. So this is not a good example for this.
So can we like have the code when you're giving the example? Can we
So
also see
first
that?
I'm just explaining the example, then we will relate to the code. Okay, and
Okay, sir.
so I'm taking some pattern, uh, like, or I'm writing a text first. Text. Okay, pattern. Like I'm taking some character change here. So okay, so here like a B, I'm taking this C, and one C here. So yeah, so I'm taking one text and pattern, AB. So first thing I'll calculate the last thing. So what is the index of this A and what is the last index of B? So A last index is 1, sorry 2, 0, 1, 2, and B index is 3. Okay, so this is the last index of A and B in our pattern. So we will start the same process reverse from the reverse side. Okay, and for the matching, and at any time when if our pattern is character is matched, so we will perform the same things. We will just reduce the both pointer to the previous character until our pattern is not finished. So this is the similar things. If our character is not matched, at that time we will just look this last dictionary and we will decide the shifting based on this. So suppose here I am just matching the first character BB. Okay, and if this BV is, so in this first case this is matched, so this second, this is also matched, this is also matched, this is also matched, all are matched. So if our all characters are matched, that means our complete pattern is matched. So in this case we will shift only one position to the right. Okay, so this is the first condition which we are maintaining in our code. If our complete pattern is matched, then we will shift one position to the right of our pattern. Okay, so A B A B. Okay, now in the next iteration, when what is the last character is C in the text. Okay, and here is B. So we will check that C is exist in our last dictionary or not. This C is exist in our last dictionary or not. So last dictionary only contains A and B. Okay, so C is not exist. That means this character is not exist in the pattern. So based on this information, we can directly skip uh, skip this character, and we will shift our pattern after this character. Okay, after this character position directly. Okay, so this time there is no need to shift only one position to the right. We will directly shifting our pattern for the next comparison after this C. Okay, so next, so after this, you can say that next position of the matching will start from like here, A B A B. Okay, so you can see that here we just reduce the 3 shift whenever character is not matched in using this information. So again, same things we will start from here. So this thing, this time this is matched, this is matched, and this is also matched, this is also matched. So in this case, we will shift one more. So
we shifted by 3.
yes, 3. Okay, so that's these things we will decide what is the length of the pattern. Based on this information we will shift. So actually we want to shift our pattern after this character C.
So
Because
if the length of the pattern is P, let's say, depending on where you had the mismatch, let's say, if the number, because we are going from right to left, let's say, whatever it is, right? So from the right, if we get a mismatch at P by 2, let's say, like the half of the string, we don't know. This is a 4 is an example. Then it will skip P by 2, wherever the mismatch was. So that is the advantage.
Yeah, correct.
Yeah. So
okay. So this is the one case. Two case I have discussed. One when our pattern is complete matched. One when our character is not exist in our pattern. Text character is not exist in our pattern. So then we are shifting completely after that. So this is the second case we will maintain in our code. And third is, or let me check another case also. So AB for the next. Okay, so AB. This is shifting from here. AB. Okay, so this is the matching position. So same things we will perform from here. Okay, so A and B characters are not matched. So at this time we will check this A last index in our pattern. So this is 2. So that means 2 index is this representing this A. Okay, so so we will decide that after shifting, this A should be so this pattern A. Okay, so this second index A should be below of the mismatch character of the text. So this last information, so I'm getting this 2. So based on this information, we will shift in that way. So after shifting, this A will come at the similar place. Okay, so that in this case, so after one shifting, that this pattern A will come below the text A. So like this A B, A B like this. Okay. So now once again this A is matched.
So like we have this A which is not matching and it is in the last keys. So we are how we are deciding how much we are shifting.
So that I will just show you in the code how we are deciding these things. So first thing, this is clear. If our character is not matched, we will just check the last index in the last dictionary, and based on that, we will decide our shifting position. Okay, so after shifting, that A will come at the above of this last index A. Okay, so after that, this is matched, all matched. Then we will get the same. Once again, after just shifting, we will check the first character, and this is not exist in our pattern, and we will completely ignore because after that there is no character. So which condition where we are maintaining in this our code? So first thing is the last process. Okay, so this last part. Okay, so this is just computing the last index of each character in pattern. After that, this is the while loop for the text. Okay, and we are just maintaining this match and J. So J is for pattern, and matched we are just taking one flag, and this second loop we are running for the pattern. Okay, and you can see that we are performing the same things. If this position is does not match this PJ. Okay, if this text character is not matched with PJ, so we will just set this match equal to false, and we will just reduce our J to J minus 1. Okay, and after that we are checking if our match equal to true or not. If match equal to true, that means we have completed the process of pattern matching, and all characters are matched. In that case, this condition will be satisfied, and in that case we will just store our matching index, and we will increment our I to the 1, because this time we are using while loop. Okay, so we are incrementing this I this time of the 1 position. So if our so this is the first condition. If our pattern is completely matched, in that case we will shift only 1 position to the next matching. So you can see here this condition we are following. So if this condition is true, we are shifting only 1 position. If so, this is the else part of if this match equal to false. That means our character is not matched at any position. So this part is maintaining this information here. Okay, so actually you can see when every time when we are just comparing this characters in the text and pattern, every time we are reducing this j equal to j minus 1. Okay, if it is matched or it is not matched, every time. Okay, if any time it is for so if our character is not matched, still we are reducing this j equal to j minus 1. So we are reducing this, so because of that we are just incrementing again in this else part. Okay, we are just coming to the position where actually our character was not matched. Now, so this is the second case. If our character which of the text which is not matched in the pattern, if it is exist in the list, what we are checking, if this character is exist in the list. If it is not exist, so you can see that we are performing else part. Else part we are performing. Okay, if our character is not matched, what we are simply doing, I equal to, we are just deciding the I equal to I plus j plus 1. So what position actually our character is not matched, that index we are reading here, and we are adding that index plus 1 into our I value. Okay, so let me just take any example for this to more clear. Maybe. Okay. So here A last index is 1 and B last index is 3. Okay, in this case. So if suppose if we start matching, so this B is matched, this here, this A is not matched. Okay, so what is the index of this? 0, 1, 2, 3. Okay, so this is for J and this is I. So I is currently at this position. Okay, so okay, I is currently at this position 0, 0, 1, 2, 3, 4, 5, 6, 7. Okay, so you can see third index is matched, but second index is not matched. So at that the mismatch character, our J was 2. Okay, so what we will do, we will just check this, what is the last so this A is actually not matched with our pattern, so we will check the position of A in our last dictionary. So what is the last index is 1. Okay, so this is the case of this not else part actually, this part. Okay,
So how is this last index taken A and B?
this is the pre-process part of this algorithm. These things we are simply traversing the iterating the pattern, and we are just noting down that for last index for each character in our pattern. Okay, so this first part.
Okay, sir.
Okay, you can see we are just iterating the pattern and we are noting down the last index in the dictionary.
Okay,
So
sir.
why are we calling this as a brute force?
This is not a brute force, this is Boyer-Murray algorithm.
Which one?
This is Boyer-Murray algorithm.
Or
This
okay.
is
I put the question back to the previous one. You were talking about a brute force, no?
yes.
Why do we call that as a brute force?
This is the naive approach actually. If
I mean,
so
my
we are-
understanding is brute force means some sort of a ruthless way of doing things.
brute force means the naive approach, simple approach. We are not improving anything. This is the or any naive approach. If you are comparing any two strings, what you can do?
Oh, okay. That's a simple one, huh?
Yeah, that's a simple
Brute
one.
force, the name is given for a simple algorithm, huh?
That's simple. Okay.
Okay.
So in this case, so actually, which I just mentioned that this case here, the A character is not matched in our pattern. So we are just looking at what is the last index of A is 1. So this is the case when we are coming inside this else condition. Okay, so this else condition, and inside this else condition, we are just moving to this if condition, because this time character is exist in our dictionary. Okay, so what are the character which is mismatched in the text? A is exist in our dictionary. So we will just decide our I based on this formula, I equal to I plus max of j minus last of this text character index. Okay, and comma 1. So what is the I this time? So I is actually 0. So I is actually 0. So we are just incrementing I equal to 0 plus max. Okay, so max, and what we are getting j minus. So what is the j value currently when our character is not matched? This is 2. Okay, so this index which is not matched with the character, so j is 2. So 2 minus, what is the last value of A? What is the last index of A? 1. So we are taking this 1 and comma 1. Okay, so in this case 2 minus 1, we are getting just 1 and same 1. So 1 we are getting. So we will, in this case, we will simply shift only one character. Okay, so we are getting I equal to 1. Why we are just taking this 1 here for the max? Because in some case there is a chance we will get the negative value here. So this j minus last of t, this if we just calculate this value, we will get the last index, sorry, negative value for this calculation, j minus this one. So in that case we will not shift our pattern, so we will shift only one position to the right. So because of that we are taking by default 1. So what is this case actually? So in this case you can see that we are getting finally one value for by the formula, and based on that we are simply shifting only 0 to 1 index. So we are getting new index for the I. This is 1. Okay. So what is the another condition when we actually get this negative value? So that is the case. Let me just figure out the case. A, B. Okay. And the another example else part I just quickly discussed. So A, B, A, C. Okay. And A, B, B. Okay, like this. So for this example, so suppose first character you match this C and B. Okay, so this is 0 index, 0, 1, 2, 3, and 0, 1, 2, 3. Now currently I equal to at 0 place. Okay, I equal to 0, and J is start with the last index of this. Okay, this pattern. Now first character C is not matched with B. Okay, and this C is not exist in our dictionary because our pattern only contains A and B. So in this case we will directly come at this else part. Okay, so how we can just decide the shifting? Okay, so we will decide the shifting on based on this.
So basically we are just shifting by the length of the pattern, right?
Length of the pattern. No, not length of the pattern. What are the current position of J actually?
So
Based on the
so because we have just started matching, right? So the current position of J will be the length of the pattern minus 1. So when we do length,
so this is the one case when we are just getting the mismatch on the first character.
Yes, on the first character.
But there is a chance. So suppose another like A, B, or like A, B, C, or B. Okay, A, B, B. Okay, and A, B, B. So this is the another case. So we cannot say the length. Actually, we are just taking the j value. So I equal to 0 this time. Okay, I equal to 0, and j is starting from this index 3. Okay, and this first character is matched in this case. But when we are just so our j will move to the second index. Okay, second index is this time our c is not matched with b. Okay, so in this case, when this is not matched, so what is the value at this time? J is equal to 2. Okay, and I was 0. So now we will decide the shifting based on this. So you can see 3 character. Actually, there are 3 character remaining, including this b. So we need to shift at 3 plus 1, 4 shifting to the right. Okay, to after completely moving to this after c. So because of that, we are just adding this I plus, so I 0.
3 characters only, right? J is 2.
Okay, so that indexing, okay, indexing is starting from 0. Okay, so 1, 2, yeah, 3 character, correct. So after 3 position shifting, this A will come after C. Yeah, this. Yeah. So if we will shift 1 position, 2 position, and 3 position. Okay, so we'll after 3 position, our A will come at this position. So because of that, we are just using this formula I equal to I plus j. So I is 0, 0 plus j. What is the j value? 2, and plus 1. So 3. So that means our I is actually shifting from 0 to 3. Index directly. So okay, so initially our I was at this position. Now after shifting, we are reaching at this I equal to at this P position. Okay, so you can see that we are completely ignoring this character and we are moving completely our pattern after this mismatched character, which is not exist in our pattern. So using this else part.
So here there are basically 3 cases. When there is a complete match, then,
yeah, one.
then the skipping is 1. That's like a regular process. If I compare it to the brute force, then it is same, right?
Yes.
The real benefit is actually when there is a non-match, then there are 2 cases. If the non-match is because part of the pattern exists, but otherwise the letter we encountered is actually outside the dictionary of last. Basically, we have a pattern and we encounter a letter called D, right? So that's not even in the last dictionary, right? So that is actually an advantage because we want to skip P steps.
Completely,
right? Right. So sorry, we are saying the length of the pattern is P and the text is T, let's say, right? So so in that case, now in this case, we cannot look at worst. I don't think we covered that. Worst case, of course, is NM because we are not going to really change it. But we can do like an average case, right?
Yes.
Yeah, that is what, like in practical uses, sir mentioned that it is better.
Yeah,
definitely it is better because in the normal use, so worst case happen in the rare cases.
So we can think about the knowledge from statistics 1 or 2, right? So if I'm looking at a document of length T, let's say, let's say an index from 0 to T, let's say all the letters are there, and then I'm taking kind of a sliding window of P, and I'm kind of looking at it, right? So let's say I don't know, we won't know the results until we finish the iteration, but let's say there are a few number of matches, right? So maximum possible matches are basically the pattern repeats. Pattern is A and then the document is A, right?
Yes.
So,
it's more like the normal distribution. You are usually going to get the average stuff. Extreme will be rare only.
Cannot be the normal, right? So what typically the thing we do is look at the distribution of each string, like in the last, basically. And it's not just a distribution. We are looking for conjugative also, right? So it's not really anywhere. So we can't even use the distribution. But one thing we know for sure, if you're skipping, either we are skipping P characters or something between 0 to P. So we can, on average, it is skipping P by 2 on the second step, if I'm taking expectation. So if I'm doing statistically, whatever is the probability, I don't know. For the second step, it's skipping by P by 2 on an average. And the third case, it's skipping by P. So from document to document, it will change. So it is very contextual to the document. because I can't have a generic case, right? So
Yeah,
that
but
is
anyhow, it's like if in best case or if it's in general case, it is better than the
Yeah,
that
brute force.
Morris Pratt algorithm. Then anyhow, it is going to be less than O of n plus m. Otherwise, like we will just use the other one. Like
ONM basically.
Hmm.
yeah.
Yeah.
O n m से better ही होना चाहिए. Like O n plus m से better होना चाहिए in the average case, not the worst case.
Yeah, so NM is a worst case actually, which we are getting using the brute force approach. So any algorithm which is getting the more efficient way compared to this brute force, definitely it is good. Okay,
So
so
generally much larger than P, typically in a real life situation, because I think Sir talked about the grep, right, in Unix, right, where you're searching, or Control F in Windows, right?
yeah,
So that actually uses this, was mentioned in the lectures, right? So so usually we have a document of 20 pages, but a string is maybe 2 or 3 characters. So if my document is 2,000 characters, and I'm searching for instance of whatever ABAB, like 4 characters. So for all practical purposes, the probability of this ratio between this is P by M is almost close to 0. I mean P by T in more cases, right? Pattern to text. So we can use that to actually create a statistical bound on what will be the efficiency gain for this. I don't think it was covered. That will kind of try to cover Corman or somebody. There may be some details on there. What is the efficiency gain by switching to this from brute force? Because it was not covered in the lecture actually.
yeah, not covered.
Yeah.
Yeah. Okay. So one another case is also remaining. So suppose if any time if this last index, okay, it is greater than the current j value, which is not matched actually. So at this situation, what we will do? So like our pattern is text is a. Okay, let me check. So B A A and A B. This is last year. This don't match. This is. Figure out this 1 second. Suppose A B. Okay, and this is matched. This is also matched, and okay. So suppose I'm taking this A and this is B. Like. So in this case, so this is one scenario. So A, B. Okay, suppose this is a text and this is pattern. So first we will start from the last. Okay, so what is the last index of A is 2 and B is here 3. Okay. In that case, if we match this, first character is matched, second character is also matched, and then we are checking for the third character. Okay, so this B. Okay, and we are finding out the B is not matched with the A, but we are checking that B exists in our pattern. Okay, so we will check in the list. So B exists in the pattern. So but the index, so what is the current value of the mismatch character of J is now 1. Okay, so we have reached at this one position. So this was 2, this is 3, and this is 0. So current we have just shifted J equal to 1 during the process. But at that time when we are getting mismatch, we are checking that B exists in our pattern, but what is the last index of B is 3. Okay, so last value we are getting here 3, and what is the J value we are getting 1. Okay, so if you just reduce this, so 1 minus 3, you are getting minus 2. So we will not shift to the left. Okay, so there is no benefit to shift to the left. So we are getting this minus 2. Because of that, we are taking this comma 1. Okay, in that case, in the code you can see why we are taking this 1 here. Okay, so if J minus last, if we are getting this negative value, so we will shift only one character.
So we could have also done like if I greater than P. Basically, it will happen when I value is less than P, the length of the pattern. I mean, length of the basically pattern. when you are initially searching, isn't it?
I less than P means?
So when I'm starting at the beginning of the document, let's say my P is like you are searching for triple A B, right? That is your pattern. Right? So this negative scenario will happen only for the when your I is less than equal to 3. Outside that, you can always there will be space to shift to the left, isn't it?
No. I is set to the 0 this time.
Yeah, 0. So that's what I'm saying. If once I crosses the length of P, in this case, length of P is 4. I mean, rather 3, rather, let's say, right, index. Once I crosses that, would you see negative values when you take J minus the last value of any of the characters and the J value? I don't think it will happen. Because J will be larger than P, mostly. And it will not happen, and all the values inside the last dictionary.
No, that is not the case, because suppose if our I is moving at this place at any time, so what our I value is here.
Yeah.
So 0, 1, 2, 3, 4.
Yeah.
So after suppose we have more strings after that. Okay, so in this case, J, this I will always be greater than J.
That is correct. So then we'll not get into that.
No, why we cannot get?
Because
suppose okay, just quickly give one example. Okay, so suppose first string is matched. Okay, and now our pattern is coming like this: A B A B. Okay, and we are just shifting this A B. Okay, so here this first value, this first occurrence will matched, or we can say that we are just taking here C. Okay,
yeah.
And C is not exist in our pattern. So where our pattern will shift directly from here A B. Now you can see what is I value. We are getting 0, 1, 2, 3, 4. Okay, so this is 4th index, and J will always be remain 3 to 0. Okay, so J is still 3, 2, 1, 0. So I is greater than J this time, but still we are getting the same situation.
Got it, sir. Thank you.
Okay. So this because of that, we are not deciding based on I and J value. We are deciding based on J and last occurrence of the I character.
Yeah, because that is where I think and the values inside the last dictionary would be the position of either, because in this case in the pattern there are 2 unique letters, right? So we'll have 2 entries or 2 keys, and the values for those keys will be anywhere between 0 to 3, which is the length of the pattern basically, right? So my dictionary will contain all values bounded between 0 to the length of the pattern.
Yes, pattern.
Right. So that's what I'm saying. So every time I'm going to subtract J and a P, I mean, that will be my skipping, and then that is where the negative could come actually. Yeah. Got it.
J and the last index of the mismatched character from the text.
Correct. So in this case, B is the worst case, right? B is always at the position 3, right? So when there is a mismatch with the B, that's the worst case. Yeah. Got it, sir.
So if any time when we are getting this type of situation, when our last index is coming after that the current position of the J, so in that case we just shift only one character to the right, our pattern. Okay, so these 3-4 cases we are maintaining. So what are the all possible case? So first case is actually when our pattern is completely matched. Okay, in that case we will shift our pattern to the one position to the right. If our any character is not matched, that we are coming the another else part, and in this case we have 2 situation. Two situation, or we can say that 3 situations. So one situation for if our text character is not exist in our pattern, so we will completely shift by this else condition. Okay, by the current J position, based on this current J position index, and we are simply adding this value into the I. And if our mismatched character is exist in our last dictionary, then we will check this condition max of this. So either we will get j minus last, this is a positive value or negative value. Okay, so if we are getting positive value, definitely we will select the max value here. So if we are getting more than 1, then we will shift by the greater value. If we are getting this negative, so we will just shift 1 position. Okay, so this 4 cases actually we are handling in this code.
Oh, excuse me, sir, I have a doubt.
Mhm.
Okay, so actually when the pattern gets matched, still we are drifting it by 1 character. So I couldn't get that, sir.
Pattern is matched, so it will match. So we are shifting only 1 character to the right. Why we are shifting? Because our pattern can be matched again by the from the second position. So suppose like in this case, so a like this, okay, and like here. So we are suppose our pattern is also a. Okay, so in this case you can see that the first character is matched, second is matched, third is matched. So we cannot skip completely, because if we shift 1 character to the right, still another pattern is also matched. Okay, so that means we are getting 1 matching from 0 index, second matching we are getting from 1 index in the text.
So we have 2 matches here.
2 matches in this case.
Okay. Yes, I got it. Thank you.
Okay, so because of that we are deciding this shifting. So this is some corner cases. Based on that we make this algorithm, which is covering all the corner cases. Okay, so yeah, these 3-4 cases we are handling in our code. So this is Boyer-Murray. I think it is clear.
Yes, it's clear. Is it part of OPP or no? Not only for NTerm?
No, not OPP.
Okay, NTerm. Yeah.
NTerm. Okay, so this is one algorithm. So here also you can see that worst case. So this is the case. Every time when our character is mismatched character is the last character of the pattern. Okay, so suppose we have this type of situation A. Okay, and pattern is like this B A. So first we will match with the first character, then second, then third, and after that we are getting the mismatched character is the last character. And in this case, B is the last. What is the last index of B is the same. Okay, so 0. So in this case, we can shift only 1 position to the right. So same things B A again. Okay. Once again, we are comparing all 4 length with each character. Okay. So in this case, every time we are shifting only 1 character to the right in the text, and we are performing all 4 comparisons from the pattern. Okay. So that because of that, we are getting n into n situation in this case. So this is the worst case of our Boyer-Murray algorithm. Otherwise, in general average case or best case, we are getting some improvement compared to the brute force approach. Okay, next algorithm is Raven-Karp algorithm. So this is also a string matching algorithm, but the idea is different here. So, sir, actually this is explained by the given of this number comparison. If you can see this number comparison, but what about if we are comparing the strings? So for string comparison, we can just decide the number for each character. Okay, so you know the ASCII code for the character. So we can just convert the each character by the ASCII code, and then we can start the comparison based on this number matching things.
So we are much better now. We know hashing, right?
Yeah, this is
Huffman code.
Hashing type. Yeah. So what actually this algorithm does? So because of that, we are giving this example where it contains the numeric value, but this is a string. Okay, so we have patterns. So we just convert our string to a numerical value. We have also convert our text into a numerical value. Then we are starting the comparison of this numerical value. So we can decide any modulo value. We can take any prime modulo value or any modulo value, and we will just check what reminder we are getting for the pattern. Okay, so 23. So suppose I am taking this modulo value like 11. Okay, for example. So if I divide this 23 by 11, what we are getting? Only one reminder. So what we will do, same modulo value we will use this for the pattern, and we will just take the same length of the pattern from our text every time. So suppose we have this number 2 3 3 3 2 3 3 2 3 like this. Okay, so what we will do, we will just select the same length of the pattern from the text, and we will just check what reminder we are getting for this division. Okay, so by 11. So for 23, same, I am getting 1. Okay, but still I am not sure that after getting the same reminder, we cannot say that that part is actually exact match or not, because in this case we can get the same reminder for two different values. So that is actually called the false positive or false matching, like. Okay,
So we have to take a large value to ensure that clash doesn't happen. Right? Large prime number.
Yes. Otherwise, we can use any hashing techniques to get a unique.
So in MLP, of course, unrelated codes, we learned 1 or 10 coding or something like that, right? That can be done.
I'm not sure about this MLP part. Actually, I haven't checked this content.
Okay.
Okay, so what happened? So 23, it is matched. So we are getting the same reminder 1. Okay, which we are getting from the pattern. So, but after that, after getting the same reminder, still we need to check our pattern. Okay, after getting the same reminder, we will compare the character also. Okay, so here after getting the same 1, we will compare the same digit 2 3 2 3 are matched actually or not.
But like, how are we converting these two numbers?
So that is actually some process to convert the character into using the ASCII code, or if you have any specific characters for like A to B, or sorry, A to C or A to D like this, you can simply convert any coding numerical process. Otherwise, in general, ASCII code is used to convert. Okay, so each symbol, each character, we have one fixed unique ASCII code, so that we can use to convert. So in this case, after getting the one match, so this is actually a correct match. After that, we will shift one position and we will select the next 2 digit in our strings. Okay, so this is 33. So then if we divide this 33 by 11, we are getting 0. So at any time, if our reminder is not matched, definitely we will ignore. There's no need to match, compare this strings. Okay, if our reminder is not same, then we will ignore completely. Then again 33. So 33, same 0 we are getting, we will not compare this part. And 32, so same, we are getting 8 or 9, remember, I think what we are getting 10. So we will skip this. 23, this time once again we are getting 1, and then we will compare the pattern. Okay, 3 2 and 2 3 once again match. So we are getting the 3 matches, all are correct matches. But some cases we can maybe, so some part of the text we are getting like 34. Okay, suppose like this 2 3 2 3 3 4. Okay, so here 2 3, when we are just calculating the reminder part for this 23, we are getting 1. So this is correct match. Okay, now 33, we are getting 0. So this is not matched, reminder is not matched, we will ignore. Now when we are calculating for 34, so once again we are getting the 1. So in this case, we are getting the same reminder, but our pattern is actually not matched. So this is called the false positive. Okay.
So here, the benefit of doing this is we are not doing really letter by letter, but basically, kind of entire window is being compared, right? So basically we're using a hashing function to get the text and also the pattern, and then we are not doing in the original thing. We are doing in the hashed space.
Yes. We are simply matching the hash thing first. If our hash is matched, then we will compare.
Yeah.
Okay, so because our hash is also similar to the two different value. If we are using any very good hashing technique, so maybe there is a less chance to get the collision. But if we are taking a very normal example, so that is actually called as a false positive. When our reminder is same, but pattern is not same.
So they were saying that for ASCII, if we have got a document in ASCII, ASCII uses a base of 256. In fact, it's used in most of the encryption, right?
Yeah.
AES 256. So 256 is the base. So they are actually talking about taking a polynomial hashing. So you basically take the polynomial, and then base is essentially like a large prime number, right?
Yeah,
Power.
correct.
Yeah, 256 raised to the power like a prime number, like 101 or something like that. So that way, your probability of a collision is actually very, very low.
Yeah, correct.
That is what they were recommending actually to. So yeah.
Okay, so this type of question is actually many times asked in the main term exam. Okay, so this numerical value is given and pattern is given. So how many
But
false
like
positive are there?
in this, we have not used the prime number, right? That remainder thing.
Yeah, in this
we have
code.
not mentioned. Yeah, in this code.
So code, code is little bit different actually. Otherwise, the concept is this. So what we are doing in the code, we are directly comparing actually. Yeah, we are directly comparing after converting to the number. Okay, so after reading the string, actually we are reading this from the string, so 2, 3, and we are directly comparing. So 2, 3
This is what we'll do if there is a false positive. This is what we'll do.
False positive.
If there is a false positive, then we have to execute this code, I think.
No, actually, this code is also providing the matching information, but we are not following this approach, which I just explained, that this reminder things. This is the another way to just compute this matching. But in this, we are not getting this information false positive or this thing.
So false positive will happen when I got basically we're like, if I compare to the previous algorithm, right? We had a last dictionary, we had a lot of keys, right? So if there are two letters in the pattern which have the same hashed value, then there is a collision, right? That's where the false positive will happen. Otherwise, if I have got let's say P letter in the pattern, I have got P unique letters, so whatever it is, let's say every letter is unique, and I've got unique expression of P hashed values, then there is no collision, right?
Yes.
So we have to just ensure that while we are encoding or hashing our pattern, there's no collision. So that we can do by these different techniques, either. But that's the ultimate goal, right? As long as if I'm searching for ABC, a hash of A should not be equal to hash of B, should not be equal to hash of C.
Actually, this code is not the Ravenclark approach. It is just showing that how we can compare the numbers. Okay, but main approach is actually just discussed later. So this multiple of divide by k like this. So you can see that this example. This is the main approach. That the initial part is explained by the sir, how we can compare the digits of this strings part actually. We just take the same length of the string pattern from the strings, and we can compare the digits. But after that, this main Ravenclark algorithm is discussed, where we are following the same approach, this modulo approach. Okay, so you can see that in the pattern and text, we are taking q equal to 13, and after that, we are just taking the remainder things. Okay. So this is false positive, must scan and validate each block of the appear to the match.
Yeah, so in this example, in this slide, we are using a small prime number, 13, right?
13,
so
yeah.
we see that for 31415, we are getting 7. And for 6799 also getting 7. That's the collision.
Yeah, correct.
we don't know which one match, but it is
So
problematic.
this is the main pattern, actually 31415.
Yeah.
Okay, so this is the actual pattern, but we are also getting the same reminder for this 67399. Okay, so same. This is actually a false positive, which is getting the same reminder 7, but still we have to compare our pattern and text after getting the same reminder. But if we are not getting the same reminder, so we can completely skip. There is no need to compare. Then.
So according to a brute force, the outer loop is fine. The inner loop, we know how to do it if there's unique hash key, because the inner loop was essentially to compare letter by letter to see if it is actually matching or not, right? So in this case, in this algorithm, it is actually eliminating that inner loop. It is not doing character by character. It is doing that entire block or window in one go.
So upper loop is running for selecting the each length of the pattern. Actually, we are running the upper loop, but inner loop is actually skipping after getting the reminder. After getting the reminder, if reminder is not matched, then we are directly skipping that. We are not matching the each character. Okay. So this code is actually just discussed before this algorithm. So that is actually simple matching the digits of the pattern and strings. Otherwise, I think one second.
So best case for Rabin curve will be n, right, sir? Best case will be n, and worst case will be nm.
Pre-processing, so this time is actually explained. N plus m, or if n is greater than, very greater than compared to the m, so we can say that n. Worst case is still this nm. So what is the situation of worst case? If we are getting the same reminder every time, but we are getting the false positive.
But if you are getting different reminder every time, then the best case will be n, right, sir?
So this is given here, n plus m or n. If our n is greater than to the n, you can see. Okay. So n plus m, why we are written this? Because anytime if our pattern is matching, so still for the false positive, we are comparing the character by character, na? So because of that, we are getting the m also. In this. So otherwise, still we are improving our total time. Okay, so that algorithm is given here. You can see that actually I added the notes. So text is given, pattern is given. So this hash function we are using, you can see. Prime, we are taking this 101. Okay, pattern hash, we are calculating the pattern hash. Okay, here. And then we are just taking one text hash value, and we are calculating the text hash for each part of the text, which is
What is
equivalent to the
ORD?
pattern. This is the simple function. Okay. This gives this things sk value, I think.
Okay.
For each text, it is giving the sk value. So let me check in the compiler 1 second. What is?
It's a Unicode for given.
Unicode.
So for Robin Moore, it was order n by m. This is n plus m, right?
Why n by m?
So the average case I'm talking about, not the worst case complexity.
Okay.
I'm talking about average because obviously we can't take worst case as nm, right? So we're taking the average case, which is probably more practical usage.
Yes.
Where more was n by m comparisons, right? N is kind of the length of that, or maybe t by t, whatever you want to call it, right? The length of the text divided by the length of the pattern, basically, right? That's my order. Now for Robin Corp, it is order of n plus m, length of the text plus length of the pattern.
Yes, correct.
So obviously when we compare the average case, because we are talking about average case in this case, so looks like Burr-Moore is more effective, but intuitively we know Robin Corp is that rabbit, whatever it is, has function and it should do less work. So that was a little perplexing in the sense by taking more efficient. How is the average case turning out to be order n plus m? And also another thing is when we are searching for a smaller substring, looks like the recommendation was to use like Burr-Moore, but if it is like a large string, right? I don't know what does that mean. Like, is it like 10 characters or 15 characters? Then I think this one is more effective. So again, no proof or whatever. It's just more recommendation. So we don't know. We'll have to still go through it. It was not covered in the lecture, sir.
Yeah, you have to check the book for the detail. I think Corman or this.
Yeah, sir. After the interm, Corman it used to be scary now. Before this.
Yeah. So this algorithm is given on the notes. If you want to see the main Rabin-Karp algorithm for the actual text and patterns, you can see this implementation. So how first we are simply getting the this ASCII value for each character, and we are just calculating the hash for the pattern. And same things we are doing with the text for the same length of the pattern, and then we are comparing this. So you can see in the condition line number 21, if our text has equal to pattern has, and the first condition is true, then we are also comparing our text length equal to pattern. So you can see that in the next part we are also comparing the pattern. Then we are adding this into our result. Pattern is matched. Okay, if first condition is not true, so second condition will not be executed. If you know this end condition, so if first condition is false, second condition is generally not evaluated. So this line number 21 and this one. So this is the main approach of the Rabin-Karp. Okay, it is clear. Rabin-Karp.
Yes, sir.
Yes, sir.
Okay, so to just implement this code also, so you will get more idea about.
ORD gives what, sir? ORD gives the
ASCII code, yeah. Unicode, or we can say that. So you can see that we are getting 65 for A. Okay, and for B you will get 66. 66. Okay, so yeah, this is the second, and this third algorithm is KMP algorithm. Okay. Yeah, so KMP algorithm is actually used the prefix or suffix information from the pattern to reduce the shifting. And what is this prefix and suffix things? So first we will discuss this prefix and suffix things. What is the meaning? And the first pre-processing part of the KMP is to calculate this fail function. Okay, so this fail function is actually calculate this prefix information which is matched with the suffix of the pattern. So I'm taking one example. What is this represent actually? So suppose we have one pattern like this: A, B, A, A, B, A. Okay, so this is one pattern, and if you see that if you check this part, first part and the second part, so here prefix suffix, you have already learned in the week 9. I think this part is okay. So prefix for any strings like A, B, B, what is the prefix of this string? Like we can say that A, or we can say that AB. Okay, so A is also prefix, AB is also prefix. we generally not take the complete string as a prefix. Okay, so A is prefix, AB is a prefix. And what is the meaning of suffix? So for the same strings A, B, B, we can see that B is suffix because B is coming at the last. And if we increase the length, so B and B is also a suffix of this string. Okay, so I hope this is clear what is prefix and what is suffix of any string. So in our pattern, if any part of the string which is a prefix and which is also a suffix, so that things actually we are calculating using this fail function before in the pre-processing part of the KMP algorithms. Okay, so this ABC, you can see that here ABA and ABA both are, so this ABA is actually a prefix of the pattern and this is also a suffix of the pattern. So both things. Okay, so we will find out this information for the each part of the pattern, not only the one. So suppose if I am just calculating again, so ABA, ABA. Okay, so if we are taking only the first part of this pattern, so this is a single length, so there's no need to check for this suffix and prefix part this. Okay, but if we are taking the length AB, so is there any part of this AB which is a prefix and it is also a suffix? Just look only AB.
A is a prefix, B is a suffix.
So just check that A is a prefix, and suffix is a B. So you can see that prefix and suffix are not matched. So only these two, the single are possible. Single prefix are possible, single suffix are possible, which is actually not equal. So that means there is no prefix which is also a suffix for this part AB. Okay, when we increase the length ABA. Okay, now in this part, so suffix, if we note down the suffix and prefix, so suffix we are getting A and we are getting BA. Okay, and prefix what we are getting A and AB. Okay, can you see any common part? So this A is common. Okay, so in this part, this A is actually common, which is a prefix and which is also a suffix. Same things we will increase more. So A, B, A, A.
The worst case will be when we are searching for a palindrome in a text.
Yes, correct. But we can do in the order of n time these things. We are calculating this information in order of n time in the fail function. In this part you can also see, so A is prefix and A is also suffix, so there is one match. Okay, apart from that there is no prefix and no suffix which are matched. Okay, because here if you take AB or here you are taking AA. Okay, if you increase the more length ABA and then BA, so not matched, only AA is matched. So this information actually we are calculating in the fail function of the KMP algorithm. And how we are calculating, and we can simply calculating by the length. So I'm taking the same example, AB, AB, A, AB, A. Okay, so for the same length, okay, so we are just maintaining a list for each character. Okay, so for when we are just considering only a single character, so at this time there is no prefix which is also a suffix, so we will just mark as a 0. Okay, so when we increase this AB, okay, still we are not getting any matching which is a prefix and suffix, so same 0 till this B. Okay, so AB. Now when we are just moving to the next ABA, okay, this time you can see that what is the length of the prefix which is also a suffix. Length, I am asking the length. In this case ABA
1.
Yeah, A. So this A and this A. Okay, so length of this A is 1. So,
So this automaton is basically this prefix suffix.
Sorry, can you repeat?
Sir was calling it automaton.
That was the example, I think.
Okay.
Because this name I haven't listened. Let me open the slide 1 second. KMP.
You mean the automata?
Oh, that automata. Okay, you're talking about.
Automata. Yeah.
Okay. Yeah, actually, that things are explained by this finite automata. That is actually very deep topic, and that is actually one course, finite automata. This course. So, sir, just explain this prefix a suffix part using this finite automata. If this part is cleared in the KMP algorithm, so I think that this finite automata part you can skip. Otherwise, this is very deep topic. You will confuse in this because you have to learn lots of things to understand these. Okay, so to understand this complete finite automata, you have to just learn all the this state and this transition state, and there are two types, DFA and DFA. There are many things you have to learn.
Turing machines.
That also next part. So that actually, sir, is also explained this suffix and prefix things, which we are just discussing in the KMP algorithm. Sir discussed these things in the finite automata. So same finite automata is actually used during this pattern matching. Okay. So now you got what we are actually calculating here. So same things, A, B, A, A. Okay. So the next, when we increase the same length, A, B, A, A. So till this part, what is the length of the prefix, which is also a suffix? Okay. So what is the length? A and A, only one. So we will just keep as a 1 here till here. Now when we increase one more, so A, B, A, B. Now just look prefix. Okay. So what is the prefix possible like? If you note down all, so A, B, A, B, A, B, A. So all these are prefix, and if you note down the suffix, so B, A, B, and B, A, B. All these are suffix, okay, and these are prefix. So what are the length of the prefix, which is also a suffix?
AB.
Okay, so maximum length. Okay, so you can see that AB. So the length of is this 2. Okay, so we can write down 2 here. Okay, now we increase the next one more. So A, B, A, B, A. Okay, in this case, you will get the 3 length, which are actually a prefix and also a suffix.
So it's the longest prefix, which is also a suffix, right?
Longest prefix. So in this case, you will also get the A, okay, which is matched. But we will just select the longest prefix, which is also a suffix. So 3. This time we are getting 3. So this information we are calculating using a fail function. So this did things. Okay, so this is the first part of the KMP. If this is clear, what we are just calculating in the pattern.
So that automata thing, that fail function.
This fail function, I'm not talking about any automata things, and just also don't go in that topic. Automata, that is actually also we are calculating the same things by using the finite automata. Okay, but here we are calculating by using simple code.
So the complex case will be if I take a palindrome and my string is my string is a double palindrome and my substring is a palindrome. Right? That's the complex case, like a race car. Right? It's a double palindrome, and let's say CC, the last in the middle, the 3 elements. Right? That's a palindrome. So if I'm searching for a palindrome inside a double palindrome.
Okay, I'm not getting this.
So let's say a word letter race car. If you write race car.
Okay.
Yeah, it's a double. The whole string is a palindrome. car, right? And we are searching for CEC.
Okay. Yeah. But that is not relating to this topic, I think. We are not searching. Actually, we are just noting down till this index. What is the length of the prefix, which is also a suffix? So this length is actually we are maintaining at this place. And we will use this information to reduce the shifting in KMP algorithm. Okay. So I think this calculation part is clear. This type of question is also asked many times in the end term exam. So one pattern is given, what is the field function value will become. So you no need to remember the code for that. That is simply you can just check the maximum length of the suffix, which is also a prefix, till every index, and calculate the value for that. Okay, so you can calculate manually this, and we are doing these things by the code in the KMP algorithm in the pre-process part. And after that, how we are just reducing the shifting using this information. So like our pattern, so for the same pattern, if our suppose if our text is ABC, okay, we figure out this text. So A, C, is matched, right? Okay, and A, B, A, A. So suppose this is a text, okay, and this is a pattern. So if we are comparing this, so you can see from this first position, okay, if we are comparing this first position, our pattern character is matched. Okay, second is character is matched, third is matched. Okay, now this time our character is not matched. So in this case, if we have matched with this ABA part with our last part, suffix part of our pattern, okay, and this C is not matched in this, and C is not exist in our pattern. So what we will do? So is there any need to compare this ABA part to this prefix, because this is also a suffix. If we this part is already we have checked with the suffix part of the pattern, that means this is also matched with the prefix part of the pattern. Okay, so if we are getting the after comparing this suffix part, if all are matched, if we are getting any unmatched character, so we can shift our pattern like this. So we will shift our pattern similar to on this line ABA, and next we will move to this ABA. Okay, and we will start comparison from this character. Okay, let me just quickly check the code. This time I think we used from the left to right. One second. This is field function, and this is called PJ. Okay, so okay, this KMP algorithm we are using from left to right comparison. Okay.
So, like, can you explain the like when we are actually checking in that, like, so how is that working?
First thing I want to clear that how we use this suffix and prefix information to skip the our pattern actually. So actually I was just comparing from the last, but algorithm used from the left to right.
So I'm getting the fail function.
Ha.
Then how are we comparing?
So that I'm just looking this. Okay, just quickly check this. So after getting the fill function, we have done here 0 0 and TJ we are matching the character KM minus 1 match up and Sam and else part LFK fill function. Okay. I have to take another example then. Text equal to A B A B C like this. A B A B This is matched. This is matched. One second. This is still confusing.
Sir, I gave a couple of strings in the
chat.
Yeah, there was a good example I had encountered. So
okay. A B C A B C A B C A and pattern is A B C A B A B C B A B C. Okay. But in this case, I think the pattern is completely matched. The first case.
Yeah, so 0 is the answer obviously to start, but there is one more also.
But we will, in this case, we will shift only one position to the right.
Yeah, first one is just like then maybe the next one that appears. That's not trivial.
A B C A B A B C. But okay, so B is not matched. The first character is not matched. Still, we will shift one more. Okay, yeah, we will reach that, I think. Okay, so A B C A B A B C. Once again, this C and A is not matched. Once move to the next A B C A and B A B C. This time we are comparing this. A B C and A B C. Okay. Okay. Yeah. So in this case, so first we will calculate the fail function for this A B C A B A B C. So 0 and 1 and this C. Sorry, 0 and 0. And for A we are getting 1, AB we are getting 2, ABA once again. So this A length. 1, and for AB we are getting 2, and ABC we are getting 3. So this is the fail function for this pattern. And in this case, first character is matched, second is also matched, third is not matched. Something is missing, not in the correct example. Let me quickly figure out the correct example for this. The code. GT is equal to DT minus 1.
There is one more instance at position number last part actually. The string I gave.
Sir, I actually found a good animation for this. Should I share?
Animation.
Oh, yeah, put the link.
Otherwise, I have just the example. Let me just figure out this.
Sir, actually, the whatever I pasted, if you read backward, it also matches. So on the chart, maybe there's a
2-minute video.
Chat. Okay, so that example, yeah, I am looking, but we are not getting this benefits of this fail function.
Yeah, fail function.
By this example. Let me quickly figure out. I see this is this match. I'm taking out A, B. Match. This is better. Maybe ABC. AB. So I think we will get some here. So here this is matched. This part is also matched. This is also matched. This is also matched. This is also matched, and this is not matched. Okay, and this character is not matched. So till now, what part is actually matched? You can see this part. Okay, so this character is not matched. So we will look from the previous character, and here, if you see this, so this ABA, this is also a prefix of this string. Okay, and if this ABA is already, we have checked, which is already matched with our suffix part till now. Okay, so that means this part is also matched with the prefix part. Correct? Because if you see this, what is the length of for this A? When our character is actually not matched, C and BA is not matched. Okay, so we will look just before the character. What is the fail function value for this A, which is 3. So we can see that till now, till this, our 3 length pattern is actually also a suffix of this pattern. So this suffix of 3 length is also a prefix of this pattern. Okay, so how we can skip this? So what will be the shifting in this case? So this C is not matched. Okay, so
like if we are comparing with this pattern, so C is not matched. So like fail function pe we'll see, right, कि B का value क्या है?
No, not B. Just one character which is matched just before this.
Okay.
Okay, we will check the fail function value for this A. Okay, so here you can see that we are getting 3 length. Okay, so this is representing that. So length of this till this part. Okay, so this is the length, which is also a prefix of this pattern. The same length, 3. Okay, and if our this part is already matched in the text, so this ABA, this part is already matched with the suffix till this A. So that means this part is also matched with the prefix of this pattern. Correct? So this part, this after shifting, there is no need to comparison to this part, and we will directly shift this. So we will shift this A below this A B C like this A B A. Okay, and we will not compare this again. We will not compare this part again because this is already matched by the suffix of the pattern. Okay, and that is also a prefix. So we will not compare again, and we will start comparison from the same character which was actually not matched. So we will start comparison from this character. Okay, so in that way we are skipping our shifting.
ABA BAB na sir. ABA BAB na.
ABA BAB, ha, yeah, correct.
So that whatever you have written here is different. So I got confused.
No, this part, just look this lower one.
Lower one, ABC ABA you have written.
No, ABA. Where is C?
Yeah, this is the one that you have put in the bottom part.
Bottom
below that ABC.
That one? Ha, so that is okay, miss.
Yeah.
That's it. And B, sorry, B, A, B. Yeah, that is actually not incorrect. Yeah, so this is the shifting, but we will not compare this part again. We will directly start comparison from this mismatch character.
But sir, Knut Morris will be efficient here, na? Because C is not present in the pattern. So directly we'll shift forward only.
Yeah, in this case, C is not exist.
Moore algorithm will be more efficient, na? Because C is not present in the pattern. So it will directly shift forward.
Yeah, so this is just an example. So this is there may be another situation. So suppose this character is a. We can take this as a also. Okay, this is so in this example you can see how we are shifting and how we are starting the comparison from the next character, not from the first character after shifting. So this part is clear or not? Just explain again.
Yes.
1 second.
So each character you have to compare only once.
Not once. 1 second. ABA. This is text and this is pattern. So this character may be A, not C. Okay, so just don't confuse about this. But actually this is a mismatch character. We can just simply taking this. Okay, so what we are doing, we are simply starting comparison from the first character. Okay, and we have calculated this as a fail function. Okay, fail function is okay. From first character 0, second character there is no prefix suffix 0, and till ABA we are getting 1 length maximum, and when ABAB we are getting 2. When we are getting ABABA, so we are getting 3, and when we are getting ABABAB, so total 4 length. Okay, so this part is also a prefix, so 4 length. So this is the fail function, and when we are comparing this pattern with the text, so this is okay. This first is matched, second is also matched, third is also matched, fourth is matched, fifth is matched, but this is not matched. Okay, so when our character is not matched, so we will look just before character. Okay, so this B is not matched, so we will look for this fail function for this A. What is the fail function value for this is 3. Okay, this 3. Then After that, what information we are getting? We are getting this information. That means till this A, 3 length of the suffix, which is also a prefix of this pattern. So that means this 3 value, it is representing this information. Till this A, B, A, B, A, we have 3 length of the suffix, which is also a prefix. Okay, so this is information. And if this 3 length of suffix is already compared in the text and matched, okay, so this part is already matched with this suffix, so that means this part is also matched with the prefix, because both are the same, prefix or suffix both are the same. So if ABA of the text is matched with the suffix of this length 3, so that we can see that this ABA is also matched with the suffix of this pattern of length 3. Okay. So based on this information, we will shift our pattern in that way. So this part, prefix part, will come below this matched part of the text. Okay, so that means after shifting our this prefix part A, B, A, this part will come below this matched part, and remaining part will remain same. So P, A, B. Okay, and we will not compare this part again after shifting. We will not compare this part again because this is already matched. We know this information by using this fail function, and we will not compare A again, B and B and A again. We will start comparison from this character. Okay, this time this A and B is not matched. Okay, this is not matched. Once again we will check what is the fail function for this A. Okay, in this case, what is the fail function for this A? So you can see that 1. So that means 1 length we will choose to the shifting. After shifting, so this A, actually you can see that if this A is matched with this A, okay, so that means this is also matched with the prefix of the pattern of length 1. So after shifting, this A should be come below this text A. Okay, so that means shifting will be happen like this: A and B, A and B, A, B. Okay, but we will not compare this character again. Okay, so because this is matched already with this, we will start continue comparison from the mismatched character. So this A and this next one. Okay, so this B, once again this is not matched. Okay, so this A and B is not matched. So in this case, what is the so this is not matched, so we will check for the fail function for this 0. So in this case, we will shift only 1 character. In this situation, we will shift only 1 position to the right. So A, B, A and B, A, B, like this. Okay, so in this case, once again, so first character is not matched. So once again, first character is not matched. So same thing, 0 fail function we are getting. Or there is no character before this, so we are not checking this, and we will shift 1 more again.
First is match, no sir, A and A.
Okay, sorry. Yeah, A and A is matched. Then second character is not matched. Okay, actually, so A and B. Okay, but we will check the fail function for this A, and which is 0, and we are getting 0. So same things, we will shift only 1 position to the right. So A, B, A and B, A, B. And here you will get the matching. So A, B, A, B, A, B. Okay, so all match. You will get the matching from here. So initial part, you can see that we reduce some comparison. So first thing is the shifting part. We directly shifting in that way. And after shifting, we are also not comparing the again. That part we are not comparing again. Okay, so ABC after shifting, we are not comparing this part again, and we are starting comparison after this part based on this fail function information. So that things actually we are doing in the code. Now if you see the code, so first thing is we are running from the both 0 index J and K. So J is representing the length of t text. Okay, here j we are using for the text, and this k value. Okay, k value we are using for the pattern. Okay, so yeah, if any time during the comparison, if our k is reaching at this index m-1, okay, so if our k is equal to m-1, so that means we have reached the last character, and so if tj equal to pk, so that means if this condition is true and our k is reached at this last index, so that means our complete pattern is matched. So in that case, we will just record this in our data list match, and we will reset our k equal to 0 to start comparison again, and we will just shifting this j in the text. Okay, so in this j we are using for the text, and we will shift our j based on this condition. So j equal to j minus m plus 2. So in this case, when our text is matched, so you will get the same only one value above. Okay, so in this case, so this j minus m plus 2, actually you will get the one shifting using this.
So you shifted by 1.
One, you can see that for the current value. Okay, so after that, else part, if this k is actually not reaching this last length, what we are doing, we are simply incrementing both j equal to j plus 1, k equal to k plus 1. That means our character is matched, but we are not reaching till the last character of the pattern. So that is actually else part. In this case, we are simply incrementing both pointer to the next character. So j equal to j plus 1, k equal to k plus 1. So this is the else part of this. So else part of this, if our character is not matched, okay, so tj does not equal to pk. If our character is not matched, so we are coming on this elif part. Elif part, if our k is greater than 0, k is greater than 0 means what k is representing? K is representing the index of pattern, or that means k is greater than 0 means our unmatched character is actually not a first character of the pattern. Okay, our unmatched character is a maybe second, third, fourth, fifth, or anything, but not a first character. If it is a first character, we will simply going to the else part, and we are incrementing only 1. You can see that we are incrementing our j by 1 position to the right. Else part. Okay, if our first character is not matched of the pattern, so we will shift only 1 position to the right. But if our k is greater than 0, that means our maybe second or third or fourth character is not matched, then we are looking the fail function value. Okay, then we are looking this fail function value for the k equal to fail of k minus 1. Okay, what is the k minus? You can see that we are just looking the previous value, not the unmatched value. Okay, so we are just resetting our k based on this fail function. What is the fail value of k minus 1? Okay, and we are resetting this k value. So in this example, you can see if you see this example in the first case, this 3. So here what is k actually? So k is 0, 1, 2, 3, 4, 5. Okay, so k is actually when k was 5, at that time our character was not matched. So what we are just resetting that k equal to fail of k minus 1. So k minus 1 is 4. So what is the 4 fail function value? So this is 3. Okay, so that means what is the 4 index value of the list? So we are getting k equal to 3. Okay, that means we are directly just starting comparison from k equal to 3. So you can see that where we are comparison. So after shifting, so this is 0 index, this is 1, this is 2, this is 3, this is 4, this is 5. So after mismatch character, we have start comparison from this position. This. Okay. We are not comparing this part again. And we are not changing any this j value this time. J is at the same position where the mismatch happened. but we have just set the k position. So k position we are getting from the last this fail function list, and we are getting 3, and we have just started comparison from this b position. Okay, this is matched or not. So we are just skipping this prefix or suffix part, which is already matched in a suffix. So we will not compare again in the prefix, and we will start comparison after that. So that part is actually code doing. Okay, so I hope this code is clear to you, what every part is actually happening. Is it clear?
Yes, sir.
Yes, sir.
Sir.
So in this, actually, we just reduce this comparison based on this information. Okay, so analysis purpose, a KMP algorithm efficiently compute the automation describing prefix match in the pattern P. So this is the same things. Automation means which we have discussed just before this topic, finite automation. So that part is actually we are computing by this KMP algorithm. Okay, this prefix and suffix information. After that, complexity of this pre-processing of the field function is big O m. So length of the pattern actually. If you see the code, we are just calculating in that way. So we are using only one loop. You can see while j is less than m, we are using only one loop of the m length. Okay, and in this way we are getting this information length of the prefix, which is also a suffix, this part. So we go m time, we are getting this pre-process function. After that, we are just after pre-processing can check matches in the text t in order of n time. So overall, the same things. Overall KMP algorithm works in time m plus n. So if you see the code. So if you see this code of the find KMP algorithm, we are using only one loop, j less than n, and we are not running any inside loop of this. And we are getting the detail. In the order of n time, we are performing this KMP. So total complexity we are getting m for this pre-processing part or n for this main part. So n plus m. Okay.
So now that we learned 3, right? So KMP is pretty clear. You know, when the substring or the pattern has repeated substring, right? So that is where it brings efficiency. I think that part is clear with the prefix. When we go to Boer-Moore or Ravenkart, right? I think the pre-processing part is, I guess, more expensive for Boer-Moore.
No, why the more expensive of pre-processing part? Last dictionary, which is also taking order of m time.
Yeah, so it will be efficient if I kind of use the same pattern multiple times, right, within a very large text. Let's say I have a 50-page Word document. Okay, typically I'll tell you in real life situation what we typically do in particular people who are working in working professionals, right? You have a legal agreement where we sign a non-disclosure agreement. So there are two parties. Most of the text is very similar. What you do is you just basically do a find and replace, right? So it's basically you're searching and then replacing, right? So all occurrences of a particular substring you want to replace with a global, another substitution, and that's it. So there you are searching for the same pattern multiple times within a large document. It could be many consultants also do the same, right? So that is a practical application, right?
Yeah.
So, let's say I'm trying to find, let's say I'm looking for some document in my file. Like I want to search for a pattern across multiple documents. Like, Windows, we have these search, right? File Explorer. Let's say I've got bunch of documents, right? I want to find, I don't remember the document name, nothing, right? So I'm searching for a pattern across multiple texts, right? There's another approach, right? Where you are, I think there Rabin-Karp would be more interesting.
Yeah. Yes, correct.
Not for anything actually. Your pattern could change because in the Windows will give you whatever star, whatever, right? So now that look into it, but, that seems to be like the real life use cases.
Yeah, correct. So Rabin-Karp is the useful in that. I think, yeah, correct.
What about the search engine? Search engine is also, I don't know what algorithm search engine uses. I mean, we learned about PageRank, but I don't know. That's more like a doc indexing and all that.
So these algorithms, maybe they are not using, they are using any more efficient algorithms.
Yeah.
So these are some basic algorithms, standard algorithms.
In biology, we studied, right, these APCGs, right?
Yeah, correct.
That those are all, real life. I think, people with bioinformatics background, they can probably know that, when you are searching for a DNA, right? So you have the APCGs and very, very long sequence, and you're trying to find a particular virus which has also a pattern, right? And you're trying to pattern, right? So that's another case where you're trying to find pattern if it exists or not. So there are the sequencing. Obviously, I don't know much about it, but another real life cases where this kind of used, right?
So these all are the mainly the higher studies area and research area. So,
but you talked about the plagiarism, right? So let's say, and I know we had a Mad1 project submitted and it's going through. So out of these three, I think Rabin-Karp would be basically saying if, let's say, two students have submitted a bunch of codes, right? And you kind of compare, right? The similarity between two, let's say, codes, right? So I don't know how it is done.
So if you remember one algorithm, actually in that case, we are just calculating the similarity.
Right.
Similarity. And if you remember the big 9 algorithm, edit distance.
Edit distance, yes.
Correct?
Yeah.
So that is actually also useful in this case. So what is the difference between two files, or what is the minimum distance?
That's what you're saying. Like if somebody copies something and it just renames the variable. Then, yeah, I got it. Makes sense.
Yeah. Actually, that algorithm we are using for the
plagiarism. Actually makes sense. Yeah. I think we are all mature students. I think we can discuss about it. Yeah.
So because of that, if someone if someone is changing only variable names, or someone putting this comment, all these things, so still we caught that type of submission.
Yeah. So actually we used, the Levenstein distance, basically the edit distance, for one of the real life cases where your data is coming from different sources. There are some typos or whatever, and then it's misspelling. It is used in data quality or cleaning up data, because before you do any machine learning, data cleaning and data management are first steps. So this is where you have 2-3 words and you actually compare the similarities of two words. Calculating edit distance, if they're very close, then there's a threshold. Then you combine them into one. So essentially, you can then you can look at the frequency. Then substitute the lesser frequency with the more frequently occurring word.
Can we move to tries? Like the discussion is getting very long.
Okay. Yeah. So I hope this part is clear. Okay. So try is also a different type of data structure where we actually store this word type of information, which is actually 1 second. Tree. First thing, this forms a tree. Yes.
Does this part come in OPP as well?
Big 10 is not coming in OPP.
Because
Big
there
9.
are coding assignments with there. So
Actually, we in the initial term we just take this in the OPP, but actually we generally gives only 4 questions in the OPP. So what part actually we can cover? So in general, week 10 we not take any question from the week 10. So we
Okay, so
remove this.
there will be only 4 questions. Means
Yes.
I thought there will be 5 and out of 5
No,
we have to do 4.
4 and there's no choice.
Okay. All are compulsory, right?
Yeah, all are compulsory and equal weightage.
Okay, sir.
We have released 8 question in the mock. Okay.
Yes, sir. I've
Huh.
done.
So it will be like 2 hour paper or like 1
2 hour.
But solution means I have to compare the 2 questions that will be discussed on 18th.
Solution of mock?
Yeah.
We will discuss in the Friday session.
Okay, sir.
Okay.
All the mocks?
All the problems we will discuss. I think some problem is already covered in the coding session, live coding session. If you see the week 9 problem, so one problem is I think covered. Last TP problem. So some problem is already covered. The remaining we will cover in the session. Okay, so this trie actually is also another type of data structure. This is forms actually a tree form. Okay, and it is basically used this dictionary type of things. So where some part of is actually is meshed. So suppose if you are storing this word in the dictionary. Okay, so if you see that maybe some prefix part is meshed with the many characters, so why there is need to store each word separately if some part is already meshed in the word. So we can just save this part. So you can see in this example, so beer, bell, bed, bowl, buy, sale, this team. So initially all 5 words is actually start with B. So why this B we will need to store at 5 times if this is meshed. Okay. Same things BE, if you look this BE part, so BE also similar in the 2 word. Okay. So why we need to store this BE 2 times in our data structure? It will also take more space. And so this actually trie is useful this type of scenario where we are storing this type of information, word information, and we can reduce the space by using this prefix information. Only store only one time if any character is matched in the prefix, so we will store only one time, and remaining part we will store if it is not matched with another word separately. Okay, so here you can see that the B. Okay, so one is the root node we are maintaining, and the word which are starting from the B character, we are just taking the one node for that B. Okay, so this is representing a prefix of all these 5 characters. And next character, so same things based on this information, this prefix information of each word, we are just creating a tree. Okay, which character are repeating, we are just creating a one node for that. Okay, and based on this prefix information. So first thing is the first character we are deciding. So B and another word is taking S as a first character. So we are just creating a 2 child for the main root node B and S. So this is representing that all characters which we have are starting either from B or S. Okay, apart from that from the B. Okay, so after B, so we have 3 category which is starting from E, I, U. Okay, so we have total 5 word, but out of these 3 are unique actually, E, I, U. So same things from after this B, E, we are getting 2 different word, A and L. So in this way. So you can see this this data structure. So this is creating a form of tree, and we are also storing minimum number of characters. If you count all the characters in all the words, you can see that the number of nodes are less compared to the all characters. Okay, because we are just storing prefix information only minimum number of time. This. So in this case, that is actually reducing the space. That is also reducing the searching, because you know that in the tree there is only one path from root to the leaf. You can you can if you want to traverse from root to leaf, there is only one unique path. Okay, that means you can traverse only one single word when you are traversing from root to leaf. So that things we are just maintaining in the trie data structure. So that is also reduce this the searching time. So if you see the searching time, if you have this total 8 word, so you can maintain lots of dictionary things information. So this is similar to like index things. First we are looking for the B, which character is starting from B. So we are just moving from the B child, and then we are just looking for the next character. What is the next character of the word? So based on that, we are deciding the next child, and in that way we are just deciding the path from root to leaf, and we are getting our word. It is exist or not. Okay, and using the same information, you can also figure out this prefix or suffix things. If we want to find out that this is a prefix of this word or not, so we can simply traverse from root to leaf, and we can simply check what prefix is coming till the leaf. So we can compare this information. So this is reducing the time, and to identify the last character, we just add one dummy nodes after the leaf. So this we generally say as $, and so we can add this after each leaf node. Okay, so that is actually represent the last node information. So this is the last character. So in this way, we can search any word. Okay, so suppose we have lots of word and we have stored this in this type of trie data structure. You can see that what is the maximum length of the word in your dictionary. Okay, suppose you have 100 words and the maximum length of the word is like 10 of any word. So that is actually a worst case searching time.
So all leaf nodes not having dummy node?
No, all leaf node is added as a dummy node.
No, by is not there.
No, this is not a dummy node actually. This R and this is not representing a dummy node. So this VU by, actually this is a complete word.
No, I thought that you said the dummy node is added in all these.
I think this is missed. This is not, this square box is not representing a dummy node.
What is that?
No, sir, like dummy node is not mentioned here. So these square are indicating whether these are the ending nodes or not. But actual implementation, there is going to be a dummy node attached to the leaf nodes, which are denoted by square, having a $sign or something.
Yeah, I think this square things is missing with this Y. So because we are all last character we are putting in the square box, but we missed, I think.
D is what? Direct?
D is nothing. D is just a last character of this word. BID.
Oh, L and R is left and it's not going that way. It's on the other side. It's going right side. It is L and R is not properly. Oh, what is this?
No, if you coming from the root node from any path, you are getting a word.
Yeah, that's true. But what is the last node is? Last square box.
What? This square node is just representing a last node.
Oh, it's randomly picked up. Huh?
This is this is not randomly. This is just representation of this trie, and here this is just mentioned that this is a last word. But I think this Y we skip this. Actually, this should also be a square in the representation. So don't confuse about this.
No.
Okay, so in the
Y is not a square. Next to Y, you got to put another square.
No, why? Each last character actually we are representing by this square. Okay, so you can see this word VUY.
Okay,
so we are getting this Y. Okay. Yeah. Every actually path is representing a one word.
All right.
Okay, but in the implementation part, we actually add one more dummy node which actually contain this $sign, or we can just use any special symbol which is not used to store in the data. So we can use any special character. So if you see this implementation, so we are just adding this dollar sign in the last. Okay, and we are just implementing using the dictionary, this try data structure, because dictionary is also maintaining these things. We can make a key, so we can make one single key first, and after that we can create another dictionary for the as a value for this key, and this is the another dictionary, and this dictionary contain a two key B and S, and once again we are creating another dictionary
Sir, like
for this.
all the child are the values in the dictionary, and all the childs themselves are dictionaries, right?
Yes, correct. So this is the main key. Okay, so all this is we are creating a actually dictionary first. Okay, so suppose I am just mentioning this R. So R we are creating as a first key, and inside this we are creating another dictionary. Okay, where we are maintaining two dictionaries. Okay, so first for B, and for B we are creating another dictionary, and S we are creating another dictionary like this. Okay, and for B we are same thing E and I.
There's a bunch of nested dictionaries.
Bunch of nested, correct. Okay, so because of that we are just if we are searching, we can simply search any node in a constant time. So from root node we can simply search B and S in constant time. Okay, so that after reaching at the B, then we can search any character in constant time E, I, U. So all are representing a key for the nested dictionary. So same things we are maintaining for the each child. So that means we are just traversing this tree. So if we are moving from root to any child, so that operation we are performing in constant time. So because of that, we are reducing the searching time. Okay, so this is actually improving our searching or our new insertion. If you want to add any new word, so that is also possible. So if any prefix is already there, so that we will use the same path. Okay, and if any part is not matched, so suppose any character like ball, okay, so BO, or any we can add anything, or BOY, boy. Okay, so we will just move here and we will see that O. Okay, so O is not exist in the child of B, so we will create a new child. Okay, O for O. Okay, and then O is empty, so we will add one more child, Y, like this. So this boy will insert in this current try data structure. So all the insertion operation or searching operation you can perform in the longest length of the any string. So that is the what is the maximum height of this try data structure. So that is actually a searching time required. So this increase the searching and this operation. So this type of data we can store in this try data structure, and this is implementation. You can see that we are just creating a nested dictionary every time, and we are adding as a child. So all the remaining things are just usage of this. So suffix try, so prefix and suffix part. So suffix try in ABE like this. So here you can see that we are using dollar sign for each last character. Okay, so this dollar for each part. Okay, and suffix try for AB. Okay, actually we are just creating a suffix try for this string. So how many suffix are possible? So after every suffix we are just adding this dollar sign. Okay, so what suffix is? First suffix is A. Okay, so A suffix is possible. So after A we are just adding this dollar. Okay, then BA. So you can see that B and A, then we are adding dollar. Okay, then ABA. So ABA, we are adding this dollar. So we can just maintain this suffix information for any string in a try data structure. So that is also one application of this try data structure, and we can just check that anytime we want to find out that this is a suffix or not, we can just simply traverse this thread. Okay, and we can check that this is a suffix or not. And this is the implementation of this suffix. So same we are using. And regular expression, so this is just discussed, not much important. Okay, so if you have any doubt in regular expression, that part, or we can
Actually, I haven't seen. So.
That is actually just discussed, not in the deep. So this is also if you have done this database course. Have you done, anyone?
Yes, sir, I've done database.
So if you just use this SQL query where we want to figure out that just any column names which is starting from A, like this, like characters. So we use for the searching some data, and we have some information of the text, and we want to find out the all matching related to that part. So that is actually called this regular using this expression things. If we have first character, we want to find out that all the strings which are starting from first character and all the strings which are ending from any particular character, or any strings which contain some part of that characters. So that type of things is actually done by this regular expression. So where we use some symbols and things. So that is actually used for the searching. So that some question is also given in the assignment for similar type of this. So any example, like if any like A, B. So we are just giving this AB part this, and we are just putting that this percentage sign here and this percentage sign here, or we are giving this length. Our total length is 4. First character can be anything, as last character can be anything, but middle two characters should be AB. So we are just giving some pattern, and this pattern should be fulfilled during the matching. Okay, so this middle two characters should be matched. If any string this is matched, we will return. So it may be like B A B A. So this is also fulfilling this, like D A B C. This is also fulfilling. So middle character are AB. So this type of matching is actually called this regular expression, and we use some techniques for this. So that is just discussed little bit, not in the deep. So that is also not much important for the interim exam. So if you have any specific doubt, you can ask in the upcoming session.
So Python has this RE package that also uses.
That is also regular expression. So if you see these slides, so searching for patterns. So if some information is given, like, so look the word that has sub followed by TION, these things. Okay, so before TION, this sub part is coming before this. So any sub strings which following this rule. Okay, so you can see that this sub is coming before this TION. Okay, so anything is coming in between, that is okay, but this rule should be satisfied. So this sub should be come before this TION in the string. So that will actually matched this type of pattern. So there are many examples. So finite alphabet. So here also some automata is actually used this for the regular expression also. So that is also a little bit discussed because of that. So some rules is given like A plus V. So this is indicate that either A or B. Okay, so plus means either A or B can be matched. for this. So this is also a big topic to learn. So just go through the slides and no need to go in the deep. If you, for this course, actually this is not in the deep and also not important for the end term. But still, if you have any question, you can discuss in the next session. Otherwise, still in week 10, this Boyer-Murray, Ravenkarp, and KMP and try these data structure is okay. Any query, any question?
No, sir.
Okay.
Thank you.
So Friday is our plan is to discuss the mock problems, mock OPP problems, and after that in the next week, week 11, which is last week.
So move to the last slide of this presentation.
Sorry, mock.
Please move to the last slide of this presentation.
Okay. Huh?
Before that.
Yeah.
Before that.
More. This one.
No. So this is the last presentation, na?
This is regular expression.
Just one slide before that.
This one.
Yes, sir. So, sir, here suppose we have a this power symbol is indicating the start of the string. It is saying. So suppose, sir, we have a expression like instead of NA, suppose we have AB. Suppose instead of NA we have AB here.
Okay,
NA plus
AB.
plus is written, na? Sir, just look at this.
Last one.
BANA plus dollar. BANA plus dollar is written, na?
This
Yes,
one.
yes. So instead of NA, suppose we have AB.
So
instead
that
of NA,
one.
suppose we have AB.
Okay, so you are saying that this AB and NA and this.
BA is there. BA is correct.
Okay, so that means BA,
and then in the bracket we have AB plus dollar.
This one.
And the string which we are having is say BAB.
No, actually, what it is representing that. So
suppose
minimum,
the string which we are having is BAB like that.
BAB. You are saying this?
Yes.
That will not come. Actually, this is the fixed part. Okay. This should become, but this part completely can be repeated multiple times.
But it is repeating, no, sir. AB is repeating 2 times.
No, but this BA part is fixed. So after BA, this part is where from this part is coming. So BA cannot become. Okay. Here should become AB. And then this part can be repeated multiple times. Okay. So AB, then another pattern like AB, this time. So this plus is actually representing this information. So plus means it can be repeated. This complete part can be repeated multiple times. Okay. So because of that, this NAN is coming in this.
Okay, sir.
But in this previous example, if you see this BANA,
because this is a fixed part. This is clear.
So there are multiple actually syntax we generally use this anchoring pattern. So this is one type. If you just read the another book, that they will maybe use another syntax for this.
So what does this fifth point indicate?
This one.
Arrow P dollar. What does it
So
indicate?
this is actually the first character. This is the starting character P, and then this is also dollar. That means this is a closing.
So
Okay,
what
and this is
pattern?
the starting. This is closing. So only when fixed value is given. So only this will return P.
Okay.
Okay, so this
It will
fixed
match
value is
only
given.
P.
Yes, match exact P.
Okay, okay.
Okay. So dollar is indicating that there's no sign, though there's no character after that.
Dollar is like the end, right?
And yeah, in the above one, dollar is not given. So initial BA is given. After that can be anything. Okay, so BA. So
So
this will
this will
match.
match only P. What do you say? String. Just P.
Yeah, P. Only
Okay.
P. Okay. So this thing is also come under that automata course, regular expression. In that course, actually, this is discussed in the deep. There are many way to represent this pattern. Like star is also used. So, yeah.
Okay, sir. Thank you then. We'll see you on Friday, is it?
Yeah, Friday. The mock discussion, mock question discussion.
Right, sir.
Okay.
Thank you, sir.
Then thank you. Bye, everyone. Good night.
Good night.
Thank you, sir.
Match.